Okay, let's check if this converges or diverges. I think I'll try the ratio test. So what you do is you calculate an plus 1 over an in the series here. So that is the next term over the present term. So that will equal x power n plus 1 over n plus 1 squared divided by xn over n squared. That will equal xn plus 1 over n plus 1 squared times n squared over xn. That will equal x times n squared over n plus 1 squared like that. That will equal x times n squared over n squared plus 2n plus 1, which equals x. Divide everything by n squared. 1 plus 1 over n. 2 over n. Not that it matters actually. 1 over n squared at the end. Yeah, now, when you take the limit as n goes to infinity, this will end up just being x over 1, which obviously equals x. So I think for the ratio test here, we need the absolute value of this to be less than 1. So we can say it will converge as long as the absolute value of x is less than 1. Otherwise, it will diverge. However, that's not true. It will converge as long as yeah, okay. Actually, this is a little bit sneaky. So yeah, it'll converge. Okay, actually, I need to be more careful with my language. This is an interesting one. And so this will go to x as n goes to infinity. So it'll converge when modulus of x is less than 1. It will diverge when the modulus of x is more than 1. But in the case when the modulus of x is equal to 1, this test is inconclusive. That's not to say it'll converge or diverge, it's just that this method won't tell us. However, I know that when x is equal to 1, the sum from 1 to infinity, 1 over n squared, is equal to pi squared over 6. Therefore, I know what the situation is when the absolute value of x is 1. It's convergent as well. So the inconclusive problem is gone. So we can say it will converge if and only if the modulus of x is less than or equal to 1, and then it will diverge if and only if the modulus of x is more than 1. I think the equal to 1 is the interesting situation here. This kind of makes sense, because think about it, if x is 2, then the numerator is going to rapidly grow much faster than the denominator is, I think, right? Because you'll have 2 squared, 2 cubed, 2 power 4. You'll have 2 squared, 2 power 1, 2 power 2, 2 power 3, 2 power 4. And the denominator is only going to be, let me see, 1 squared 1, 2 squared 4, 3 squared 9, 4 squared 16. The next one will be 32, and this will be 25. The next one will be 64 and 36. You see, it's rapidly growing, actually. The next one's 128, and 49. Yeah, so this makes perfect sense. If the x is too big, it will diverge. If the x is small enough, it'll converge. And when x is 1, we actually get a special case series. The infinite sum here is pi squared over 6. Yeah, that's an interesting one.